So it's a great pleasure today to introduce Arun Majumdar. He's spent the entire day here in the Seattle area, and we've learned a huge amount from him. He's a professor of mechanical engineering at Berkeley. His research is in the area of nanostructured materials, and he was telling us that he's someone who really wasn't doing energy research until a modest number of years ago when a Pied Piper essentially convinced him that his work on nanostructured materials could be turned towards one of the nation's and the world's grand challenge problems. He's the director of the Berkeley Nanosciences and Nanoengineering Institute. He's also at Lawrence Berkeley Labs, one of Berkeley's energy labs, and running the Environmental Energy Technology Division. And in September, he was named the first director of ARPA-E, which is a new agency within the Department of Energy that's focused on game-changing extramural research. Game-changing can really make a difference in the nation and the world's energy situation. Extramural meaning that, in contrast to the energy labs, a lot of this work will be done out in the academic and entrepreneurial community. And this afternoon, Arun met for an hour with a panel of scientists and engineers and an hour with a panel of investors and entrepreneurs from the region. So today, his talk is ARPA-E, Addressing the Sputniks of Our Generation. Please welcome Arun Majumdar.
Thanks a lot, Ed. It's a pleasure to be here. You know, the weather in Washington, D.C. was so beautiful that I really miss the snow out there. But it is very nice out here. It's also nice to be in a university environment again, and also in a place where there's so much of innovation has happened in the past, which is the University of Washington and the Seattle area. So let me talk about ARPA-E. And ARPA-E is a brand new organization within the Department of Energy, and I'm going to explain sort of a thinking behind it. But before I do that, I'd like to set the stage for the challenge that we're facing and some historical context. Because I think it's important to understand, I was never a history buff, but I'm becoming one. There's a lot of things to be learned from history. So let me go right into it. ARPA-E was proposed in a report that was chaired by Norm Augustine. And this report is called Rising Above the Gathering Storm. This came out in 2005, 2006. And it really looked at the United States and said that there's a gathering storm and we need to figure things out. And as part of that, it was felt that we are not taking enough risks in the area of energy. And they proposed a DARPA-like organization called ARPA-E. And if you look at the history of DARPA, which, as many of you know, has been very successful, the history is that in 1958, it was created in 1958 in response to the launch of Sputnik, when it was felt that the United States is losing or has lost its technological lead, and we need an organization that could take the high risk, high payoff approaches and look at things, leapfrog over today's approaches and look beyond today or tomorrow. So ARPA-E was modeled after that, but if I may suggest, there are three Sputniks of our generation. Certainly the US technological lead, and I'll talk about that. We have an energy security issue. We import 60% of our petroleum from areas that may not always like us. And we have the other challenge, which is greenhouse gas emissions and climate change, which in the 1970s was not an issue. The issue was about availability of petroleum and just the price of oil, et cetera, the economics of it. So given all this, let's sort of take a minute and see what the challenge is. There is something called what is called the Kaya identity. And let me explain what that means. It's a product of many things. The top curve is the population of the world, which in many ways is one of the main challenges. There's nothing we can really do about it. There's all kinds of ethical issues, but the population is growing. The next curve is GDP per capita out here, which is increasing. That means per person, we're producing more globally. The third plot is watts per GDP. How much power do we consume to produce something? And that's going down, which is a good thing. Things are becoming more efficient, we're producing more. And the fourth one is carbon per joule of energy that we emit. And that's going down. We're getting to be globally more energy or less carbon intensive. But if you take the product of the first three, you get the total power that we consume, and you take the product of all four, you take the total carbon emission rate. And something that is, everything is in the right direction except for the population. And the question is, where do we have the soft spot? Where can we actually make a difference? And certainly carbon per joule is something that we could make a difference. If you take the product of all three and then all four, you get this. The top curve is the carbon emission rate. In this case, it's about 8 gigatons of carbon per year, or 25 gigatons of carbon dioxide per year. And that's going up linearly. What that means is that the gap between the demand and the non-carbon supply, the gap is increasing. It's like, let me put it in sort of very plain English. It's like saying that your income level, monthly salary, remains constant, which is your, let's say, your renewable supply, carbon-free supply, but your credit card bill, monthly bill, increases every month. That means today, this month is $5,000, next month is $6,000, next month is $7,000, etc. So that gap is increasing, and at the end of the day, at the end of the year, you've got a huge bill. And that's the analogy that we find out here. And obviously, this carbon dioxide, the lifetime of this carbon dioxide molecule is a few hundred years. So for our practical purposes, most of us, it's there, it's accumulating, it's stored in the atmosphere. So if the carbon emission rate is linear, simple math will tell us that the carbon dioxide is nonlinear. It's an integral of that curve. And that's where we are. And if you look at climate change, and the consequences are many, I'm not going to go into that, it is really not the rate, but the actual carbon dioxide which is there. And that is increasing in a nonlinear rate. We are essentially sitting on a Titanic. And we're going into, and for a long time people said, oh, there is no iceberg. And then people said, okay, let's just reshuffle the deck chairs. And what we want to do is to turn that whole ship around. And that is a very difficult task, and I'm going to come to what approaches do we have to take the ship, and hopefully we will get a grazing angle, impact, and then move on. But as far as now is concerned, we are looking at heading it right on to that iceberg. So what do we have? Well, this is the carbon emission rate per capita for different countries. We are first, number one in that. We are right out here, carbon emission, and we have tough competition from Australia. We have GDP per capita out here and carbon emission per capita out there. We have United States out there. We got China and India and Brazil out there. Per capita, they look great. Of course, total, they don't look so great. So clearly, which path should we take for the United States is very clear. Somehow we got to go this way. We at least come to the average, if not more. But the direction, the vector, is very, very important. But for China and India and Brazil and Mexico, there are several paths to take. If they take this path versus that path, the impact is very different. And the question is, can we work with China and India to see if they could go the right path, and we learn from them, and we help them at the same time, and see if we can all collectively take the right path. And our paths are different. So this is a huge challenge and also a huge opportunity for the United States. Just to give you a picture version of this, this is the population density of the world. We are out here in this corner. I think I got it right, somewhere out here. We have huge population, well, quite large population densities on the East Coast and Europe, massive population densities in India, in this place out here, China, Indonesia, Japan, etc., and also pockets of Africa. This is the reflection of the energy consumption in the world. These are stitched satellite pictures of the lighting pattern that you see from space. And you can see that there are some really bright pockets. You can actually tell where Nile, the river Nile is. You can look at the coastline, you can see the United States, these dots are big cities, etc. What is very revealing, and it is the depiction, illustration of that different curves that I talked about, is if you overlay the two. And when you overlay, you see some mismatches. You see some places where there are not much population and there's really bright. And you also see places where there's a lot of population in Africa, in India, China, etc., where the people have not yet turned on the lights. And if they do turn on the lights the way we have, we are in trouble. So the question is, how do we enable them to turn on the right lights? We do want them to turn on the lights, but the right kind. And how do we keep our standard of living and turn off the lights of the past? And that is metaphorically is the challenge of our lifetime, of several generations. So that is on the greenhouse gas emissions, climate change, etc. Let me talk a little bit about technological lead. This is a graph of worldwide shipments of solar cells, photovoltaic cells, in the world. In the mid-90s, the United States had more than 40% market share of photovoltaics, and that's gone down to less than 10%. And we invented solar cells. So that's something to be thought about. This is batteries. Lithium-ion batteries. We have 1% of the global market share of batteries, and last year's, the Enrico Fermi Award, which is the highest award for the Department of Energy, one of the recipients is John Goodenough, who invented the chemistries that go into these lithium-ion batteries. So this is ironic in many ways. So the question is, we have a good infrastructure to be inventive, to innovative. How do we retain some of it in the United States? That's the United States technological lead. The other part is how we consume energy. This is data on buildings on the US and China. I'm comparing two different campuses, actually. It's not University of Washington. But this is University of Pennsylvania. And the China buildings are Tsinghua University and Beijing University, and a few representative buildings. And what you find in cooling and heating is that we use about 5 to 10 times more energy in the buildings. And the question is why? And what we find is that in many ways, the way the Chinese buildings are designed, and the air conditioners are wall-mounted, you can turn off when you exit a room, and the corridors are a little warmer than the rooms, which is fine. And ours are centralized chillers. And even if there's one person in this building or two people in the building, the chiller has to run during summer. And that's a waste of energy. But there's more than that. And I want to show you the data of the chiller data, of the building data. This is Philadelphia. So you see in July that you have a large July and August, you've got a large cooling load, but you also find a heating load in August in Philadelphia. And you got in January, February, you got a large heating load, but you're air conditioning in Philadelphia in February. And this is criminal. So what's happening is the building is making itself too cold, and you got to heat it, then you make itself too hot, and you got to cool it. So it's like driving your car with your brakes on. It's just insane. I can talk a lot about it, but I won't go there. But this is what is going on. I can bet you if you go around some of the buildings out here, maybe University of Washington is much more greener, but at least I know in University of California, Berkeley, there's a lot of wastage of energy. So, so we ask the question, these are some daunting challenges, whether it's climate change, whether it is how we use our energy. The whole world has to shift its way of using and producing energy. So this is not a trivial challenge. It needs some game changes. Business as usual, as we know it, is unlikely to address this issue. And if history has told us anything, we need some game changes now, and rapidly, very fast. So this is a little bit of history now. I was looking at this question, I bumped into an article in Nature as to what was the most important invention of the 20th century. And this was the turn of the century, when people were worried about Y2K. I think a lot of Microsoft people were worried about Y2K. But at that time, this was, I got intrigued by this because of the turn of the century. And I thought it was aeroplanes and nuclear, space flight, computers, and the answer was no. And that intrigued me. So the history goes back as follows. In 1898, there was a calling upon science to save the world from impending starvation. And this was by Sir William Crookes, and he was a physicist. And he had done some calculations that if business as usual went, the population is growing because of better water quality, better health care, and the population is growing, but there's going to be starvation because there's not enough food, and we can't grow food. Crop rotation is not enough, and the things in the soil, the bioorganisms, the catalysts were not enough. And if you look at food or genetic material, is carbon, oxygen, hydrogen. We get carbon dioxide from plants through carbon dioxide fixation. We get oxygen we breathe, and hydrogen we get from water. But there's one thing which is missing, that is nitrogen. And nitrogen is absolutely critical. So 1908, so Crookes set out this challenge for the chemist. He's a physicist now, telling the chemist, figure this out. Because if you don't, we are doomed. Whichever way you look at it, whether it is getting nitrates from Chile or doing something else, we are doomed because there's not enough. And that set out a whole competition between multiple chemists. Many of them went on to win Nobel Prize in other things, but they were competing. And Fritz Haber, chemist, discovered a catalyst that would combine atmospheric nitrogen with hydrogen to form ammonia. And it turns out the first catalyst was uranium. This is pre-nuclear age. 1913, Carl Bosch scaled that up in a process which also won a Nobel Prize, 2 separate Nobel Prizes, to produce ammonia to form and make fertilizers. And there's a lot of writing about it, but what is interesting, there's a book on it, Alchemy of Air. If you're interested, this is fun reading. But the world population went from 1.6 billion people in 1900 to 6 billion people in 2000. So almost a factor of 4 increase in a matter of 100 years. And that had never happened. And it touched humanity like none other, and it was considered the most important invention. We are facing the brunt of that right now because the energy use has gone up because of the population, but it saved humanity. It also was used to make bombs, which killed humanity in some ways, but that's a separate issue. Related, but separate issue. Nevertheless, the point is that this was an inflection point. It was not a linear process. This was a game changer. And if you look at history and other game changers, none of us would be here if it was not for this invention. I don't think so. The next one is the Green Revolution of Norman Borlaug, the dwarf strain of wheat that created the Green Revolution. He took that to Mexico, grew the wheat out there, then exported that to India and Pakistan. I would not be here if it was not for this invention. And look at the land use, and look at the grain production. And it had to use the fertilizers that was created by Haber-Bosch process, but at the same time, it had to grow some strains of wheat that could actually utilize it well. And he got the Nobel Peace Prize for it, for this particular innovation. And of course, in the 1950s, 40s and 50s, polio was a big deal. And nowadays we don't think about it, but I'm reading a lot of history on this, and this was a game changer in how it changed the world. This is just United States, but in the world it had a huge impact. So these were game changers which were non-linear. And if you ask the question, given the 3 Sputniks that I talked about, what pace and scale of innovation do we need now? The pace and scale for innovations needed in energy technologies today is the following. Let's take the whole 100 years of last century. There's artificial fertilizers, green revolution, transistor, aeroplanes, Wright brothers, right? Electrification, which was considered the most important innovation and deployment by the National Academy of Engineering, polio vaccination, antibiotics, all the way to internet. Take that 100 years and squeeze that into 20 years. Imagine all of that happening in a span of the next 20 years, by 2030. That is the scale of things that we need. That's a pace of things that we need. And our goal is to see if we can identify and support today's and tomorrow's Haber, Bosch, Borlaug, Bardeen, Shockley, Salk, Gates, and Jobs, etc., of the energy sector. And it is not just ARPA-E. This is broader. This is for our country, for the world. And this is what we really need to do. So how does ARPA-E play into this? We will play some role, not the whole thing. So as I mentioned, this was part of a report, and it was came out, it was authorized in 2007. I'll spare the details of the legislation, but it was to look at these game changers, creative, out-of-the-box, transformational energy research. You could define it in many different ways, but I gave you some examples that we are trying to shoot for. Of course, the success rates for these game changers are probably less than 10% or 15%. I don't know what that number is, but it's not a very high success rate. But we have to shoot for those, otherwise we'll miss the boat. So where do we start? This is the whole, I don't know if you've seen this, this is from Lawrence Livermore Lab. This is the spaghetti chart of the energy wiring diagram for the United States. Here on the left-hand side is the supply side. You have petroleum, natural gas, coal, nuclear, solar, etc. And these numbers are in quads. Quads is a quadrillion BTU, United States primary. If you add up all the numbers, it's about 100. So these are almost percentages. And these thickness of the lines represents those numbers. And as you can see, petroleum is very thick out here. Solar is 0.006. I don't think there's a font size quite representing that, but that's very small right now. You have the demand side, which is buildings out here, industrial, which is mainly steel, glass, paper, aluminum, petrochemicals, and you have transportation out here, light-duty vehicles, freight, aircrafts, etc. And this is the infrastructure in between, which is electricity generation and transmission distribution. So if you ask the question, what do we need to do? Well, we need to decarbonize this. We need to amplify nuclear and all the renewables out here. We need to reduce our consumption, and we need a smart infrastructure to talk between both of them. And that's it, right? That's easier said than done, of course. We are certainly, what we should also think about is how to rewire this diagram in a certain way and maybe connect something from here to there and things like that, that possibly could be done. So the first round of ARPA-E funding was to sort of open it up. So let's see what's out there. And what came out was quite overwhelming, I should say. And this is before my time, before I joined ARPA-E. 3,700 concept papers came in out of this open call, and it actually broke down the DOE computer system. It was not used to this kind of, supply. And we came up with a better one. ARPA-E actually came up with a better software, which is now being used in the rest of DOE. And I should say that out of the 3,700, about 20% or 25% did not satisfy the first or second laws of thermodynamics, right? But that's okay. It's okay. This was the first round. Let's just people, it's okay to get them excited. But so the real number is about 2,000, 2,500. But that's still a large number of relevant. Out of that, about 300 or so were chosen for a full proposal, and 340 came in. And out of that, only 37 were selected. Now, one would ask that, I want to say that's a pretty small number. The average funding level was $4 million. And I'm so happy, this is again, not my decision, was done before, but I'm so happy they did not break it up into 100K chunks and give it to 1,500 people. That would have been not a good idea. They gave enough money to make a substantial difference in something that they do. This is risk-taking. And they also, selected some of the best ideas that came in. And we realized a lot of ideas were not funded, and I'll tell you what we're trying to do with them. But this was a decision that was made that we'll fund the best ideas with adequate funding, because $4 million for a startup company is Series A, done. And they can really concentrate on research, on the technical side, and get themselves ready for future funding, et cetera. We also we are trying to look at our internal process to see if you want that pace in the community, technical community, we need to be fast ourselves. So we have been able to negotiate all the contracts and awards, everything, in less than 3 months. It's done. It's out there. And in fact, some of the CEOs and other PIs have told us, the private sector has told that we are working faster than the private sector. And that's a good sign. We need to just keep it up. Just to give you a few ideas, examples of what we funded, this is a startup company called Agrivida in the area of biofuels. So as some of you know, the biggest challenge in biofuels is how to break down the cellulose or lignin into smaller sugar molecules that could be then used by bugs and other things to make, whether it's ethanol, butanol, or gasoline directly. And that, of course, cows do that in their guts. Termites do that in their guts. There's a whole cocktail of enzymes that are produced. And if you want to do it at scale, that enzyme production is expensive. What these people have done is what I call in layman's language, I have to explain this to Congress and many other parts. We are non-technical people. I say putting the cow inside the plant. So these are taking the cocktail of genes and putting it in the plant and let the plant produce these enzymes, but block the enzymes till it grows, and then trigger the enzymes later on. These are called inteins in these enzymes. And so then activate the enzymes when you want it to, and then let the plant chew itself from inside. So it's a novel idea, and it's high risk. We don't know whether it's going to work. But if it works, this could be potentially game-changing for all kinds of plants, not just switchgrass, but all other, whole palette of plants. The second one is a grid-level, potentially grid-level storage, electricity storage from MIT, Don Sadoway's project. This is a liquid metal battery. And the idea out here is, if you look at aluminum manufacturing, you pass hundreds of thousands of amps in a compound and you plate out aluminum on one electrode, and there's a gas reaction on another electrode. And this is taking that and turning that around and plating two different metals in two electrodes, and then letting it form solutions in the electrolyte in between. And if this works out, and they made some prototypes of that, and they look good, but if it works out at scale, this could potentially be less than $100 a kilowatt hour of battery, and this could be large scale, swimming pool size, and hopefully gigawatt hour. Just as a comparison, lithium-ion laptop batteries is about $2,000 a kilowatt hour. Lithium-ion car battery is about $1,000 a kilowatt hour today. So this is another innovation coming from aluminum manufacturing into electricity storage. The third idea is a windmill design. As you know, today's windmills are propellers. And these propeller-based windmills have a limit of energy conversion. They can grab only about 60%, maximum 60% of the energy. This is called the Betz limit. That means if you solve the continuity, mass continuity, momentum conservation, energy conservation equation of fluid mechanics, you'll find that the streamlines expand when they go around the propeller because of that, the speed is going down, so the area has to increase for mass conservation. So the big propeller is sampling a small part, and that is about 60%. And so what they have done is a startup company called Flow Design is to use the principles of entrainment of flow in jet engines and see whether they can create a low pressure that they can entrain fluid from the outside into it so that they can expand this area beyond the 60%. They're actually beaten the Betz limit now. They've gone beyond 100%. And And of course, the other thing, as a mechanical engineer, you can appreciate this, that the load is not on the rotating element, which is on a propeller. It's a rotating element, and there are reliability issues out here. You can put the load on the stator now, and that's another advantage of that. So these are some ideas. There are 34 such ideas. I won't go through all of them. The second round of funding, very quickly, this is called Batteries for Electrical Energy Storage, and BEAST. Today's batteries are too expensive, and the range is not much. And if you look at today's investment, I'll go to the next slide. This is the theoretical limits of energy density in batteries. If you look at today's lithium-ion batteries, whether it's lithium cobaltate or manganate for the cathode, graphite for the anode, the limit is about less than 400 watt-hour per kilogram on the cell level, not even the system level. And all our current investments are going in that. There are other batteries, like zinc air, which are not rechargeable today. Lithium sulfur battery, lithium air, which are very high risk, but we haven't invested in them. And the Japanese government is investing $60 million a year, and we don't even know what the private sector is investing, probably 5 to 10 times more than that. And the practical value for engines, the gasoline energy density is much higher, but you got a 20-25% efficiency of an engine, it comes to around 3,000 or so. So if we can get new chemistries, new architectures, and manufacturing process of batteries, that would be a leapfrog over today's approaches. So this is what we're trying to look for. Carbon capture. Today's way of carbon capture is by amines. You take primary amines, you bind CO2 using something called carbamate chemistry, and then you got to heat them to get the CO2 out and in a purified form. That cost for a coal-fired power plant is about $70, $80, $90 a ton of CO2. And the price of CO2 on the market is about $30 a ton of CO2. So if someone wants to start a business of carbon capture, they start off with a loss of $50 a ton of CO2, which is a non-starter. So our goal is that, okay, this chemistry is fine, this is scalable today. Can we look at other chemistries which are low temperature heat that can be used? Waste heat could potentially be used for that, and we are looking at new ideas. The third one is I would say a new concept. This is we call electrofuels. Electricity is difficult to store. Hydrogen is difficult to store. The best way to store hydrogen is hydrocarbons. And carbon dioxide is greenhouse gas. If you could combine them to form gasoline, which we import 60%, wouldn't that be a good idea? This is trying to kill 4 birds with 1 stone. And apparently there are ways, there are pathways in biology with organisms, with our methanogens or acetogens, which could be potentially utilized. So this is high risk, really high risk, but if it works out, this could be quite interesting. So these are the 3 areas, and we're now looking at a few other areas that we plan to invest in, and that will be announced sometime in March. One thing I would say is, given what we are now, from my vantage point, I'm looking at all the ideas that are coming in, I can tell you we are not limited by lack of good ideas. This is an amazing innovation that is happening out there in our universities and startup companies, large business, national labs. This is fascinating to watch, and I'm having a lot of fun. Where are we? This is department. I won't go into the organization structure too much. ARPA-E is separate from the Office of Science or the applied offices, and I report directly to the Secretary of Energy. This is how we are looking at the organization of ARPA-E. And this is early stages. This is like DARPA in 1958. And it's very important to get it right. And we are not tweaking this. We are tinkering with this to see whether we are in the right, we are organizing ourselves properly. The way we are looking at it is that there needs to be a tension between the technology pushers and the technology pullers. The technology pullers are the systems people who integrate things, components into systems. And technology pushers are looking into science and see what kind of device or process they can develop that could be used in a system. And the program directors are sitting, I'm recruiting right now, are sitting on the periphery. So for example, there could be a program in thermal science or materials program or chemical information science and device engineering. And they're looking at, and here are the pull people, their systems, buildings and appliances, transportation, transmission distribution, all the way to water and agriculture. And then someone out here has to then convince some of these people that if they develop a device, they will actually be used somewhere. And these people out here have to start working with these guys out here to figure out what devices to integrate and how to integrate. This tension is very important, I think. And there needs to be an upstream version of R&D investment, which is the pushers, and downstream version. That balance, I feel, is very, very important. In the process, we're trying to break down all potential stovepipes, encouraging debate. There's each program director, when they pitch a program to me, they prepare a presentation for 30 minutes, and they're there for 2.5 hours. Because it's the debate and the discussion, not just with me, but my whole team. It's like a partnership in a venture capital firm. And then we decide on the technology, decide program topics. Just the program criteria, and some of you this might be important. What do we ask? What do I ask when we want to create a program? The first thing we ask is, what is the global landscape of the field? Global landscape of the field. Science, technology, markets, players. Who are the buyers? Who are doing the good science? What are the major gaps and white spaces? Are there gaps in the markets? Are there gaps in science? Have you coordinated with the rest of DOE? If the rest of DOE is doing it, we shouldn't be doing it. What's new and why is it a potential game changer? What are the stretch goals? Are we framing the question properly so that we can create the stretch goals? And we're not picking technologies, we're picking targets. Is there room for left field ideas? Can your goal be reframed to achieve a better outcome? If you're trying to clean water and you're trying to do carbon capture, can you combine them and do both simultaneously? Wouldn't that be better? If successful, what potential impact can it make in terms of quantitative metrics? Everyone has to give us number, at least estimates, because those 3 metrics are what Congress has told us. Tell us you have to do energy and security, reduction in greenhouse gas emissions, a technological lead. Who will adopt this technology? Who are the customers? This is very important, and this is one of the differences between DARPA and ARPA-E. For DARPA, there's DoD, who is a buyer. For us, the buyer is the whole market. It's in the private sector and the public sector. Will it scale in cost and volume? If you're trying to make a catalyst out of ruthenium or osmium, you have to think about it again. Maybe you should try iron. And that might be, if you could do it, that'll be great. What instruments do you need to downstream for scaling? And are there non-technical barriers, like policy barriers and market barriers? So we look at that. Who are the potential teams and players? Is there an innovative ecosystem, a community out there that can come together and actually develop something which had not been developed before because they hadn't come together? Is the ecosystem, the community ripe? Is there a critical mass? What is the potential risk profile and time horizon, and how much will it cost? What's your budget like, and why? So these are the questions that all the program directors have to go through. And I wanted to share this with you because you might like to think about this when you're proposing something to ARPA-E. Let me just say that there is a new program that we're creating, and being from academia, this is something that I've seen happen, transitions happen in academic community amongst the students and postdocs and undergraduate students and postdocs and graduate students, et cetera, is that the student community has, I don't know how many students I've had come knocking on my doors, I want to work in energy, tell me how and where. And I'm sure that's happening out here in other universities as well. This is a huge strength that we have in the United States, because I'm not sure this kind of thing is happening elsewhere around the world. So we have created an ARPA-E Fellows program for people who are recent PhDs and people who are senior to come and spend a few years in ARPA-E. This is not a fellows that will give you a fellowship and you go do research in the lab. There are others, but this is to form a think tank internally to DOE, to be the think tank with muscle, because there are dollars behind it, potentially. And to look at our current portfolio and step back and see what are we missing? How could we do things better? So this is, these are potentially the future rock stars of energy, and that we want to bring them and serve the nation for a few years, and then they go back and do their own thing in private or public sector. Managing expectation. Everyone expects the ARPANET to come, the equivalent of the ARPANET to come from ARPA-E in the next few years. And it's very important to say that that's not going to happen in 2 years or 3 years. This happens, I mean, if you look at the history of energy change in energy, whether it's fuel and others in the United States or in the world, it has taken decades to happen. So if we are to be successful, if we are to hit the home run and create the equivalent of the ARPANET in energy sector, it'll take about 20 plus years, 10 plus years, 20 plus years for it to make a huge impact. So we know what it looks like 20 years from now. It'll change the projection of IPCC, it will shift the McKinsey curves, it'll create jobs, the market share will be huge, all kinds of good things. And we know what we're doing now. We're trying to recruit the best people. We have 3,700 concept papers. We have a new organizational structure. We can talk about now. The question is, what is the connection between the two? And the 3 to 5 year metrics are probably the most important ones because they provide the trajectory towards those home runs. And I won't go into the details of that, but here are some. If you have invested in a technology, has there been a follow-on investment post-ARPA-E award? If there has been, especially from the private sector, that's a good sign. Increase in value of a company that we invested in. How many companies have we created that if you are taking from science and we are now developing a technology that is useful to someone, maybe someone will create a company. How many have we created? If you have invested in a space that no one has ever invested before, and because of our investment in a startup company, there are 5 other startup companies that got invested in, that's good. That's competition for our own investment. That's a good sign. So these are the kinds of metrics that we're looking at. Accelerated market entry. If you can help that, that's great. And of course, patents filing, license, et cetera. The last one is help identify mechanisms of scaling innovation within the United States. And this is something that I've been thinking about. I'm talking to a lot of people. How do we scale the innovations, some of the innovations that we fund upstream, some of it at least in the United States? Because it's very easy to see the scaling happening elsewhere. So to look at that, we are looking at, if you look at historically, the change in energy is slow. Energy is a commodity and it's ubiquitous. Systems can last a long time and we have to displace an incumbent. So we're looking at the risk profile within the Department of Energy. You have the risk on y-axis and you've got, in a DoD language, technology readiness level. So Office of Science is all out here. This is high risk, sometimes exploratory research. Applied Office is out here. These are the venture capital, private equity, your government procurement, and you've got loan guarantees. ARPA-E's goal is to look at this side and see how we can accelerate that fast to the private sector. And this has to do some of it with upstream, some of it downstream, and the balance between that. But this pipeline is not perfectly understood. We had a long discussion today about this. What are the tools that we have to rapidly take it from the lab and enable people to make money out of it, frankly? So this is something that we are looking at. There's a ARPA-E Energy Innovation Summit. This is the first such thing that the DOE has actually put together. And this is jointly being done by, this has really been organized by the National Venture Capital Association, Kaufman Foundation, as well as CTSI. And to bringing the best people and a lot of people in this country, for all the stakeholders, whether the science and technology community, the investment community, both small and large, as well as the government side, both on the the executive branch and the legislative branch, Congress. Bring them together, so let's talk about this, because this is important for the nation. We are seeing a lot of great ideas. We're not limited by ideas. How do we now how do we scale some of these in the United States? So this is also a showcase for ARPA-E technologies. We are providing a platform for PIs who did not get funded by ARPA-E to bring them back and showcase them so that other funding agencies, both within DOE and outside DOE and the private sector, can look at them and see if there's value and invest them. So we realize that ARPA-E is not going to be able to solve all the problems, but we need a larger community, and that's what we're trying to build. And as I said, we're engaging the stakeholders. Let me end by a quote by someone who made this quote in a very different time, but it's absolutely apt for these times. This is by Martin Luther King. We are now faced with the fact, my friends, that tomorrow is today. We are confronted with a fierce urgency of now. In this unfolding conundrum of life and history, there is such a thing as being too late. Thank you very much.
So we have 10 minutes for questions. There are microphones. So if I could ask you to put up your hand and wait till a microphone gets to you after Arun calls on you.
Sure.
Thank you, Director Lucidon. Thank you. Very interesting. A lot of the technologies that we need to develop depend on resources. You mentioned lithium in particular. There are others, such as rare earth elements. China, in particular, is moving to restrict the export of those things and keep the development of devices using those resources internal to their country. You didn't address the resource constraints a lot of this innovation will require as we move to commercialization. Could you speak to that?
Yeah, we think about that quite a bit. In fact, if you look at our funding opportunity announcement, there are statements out there about rare earth elements and how much are we going to use, and if you're going to use rare earth elements, what's the research in the world. So we are aware of it. We are appealing to the PIs who are writing the proposals to think about it as well. And as I said, I mean, our goal, if you look at the funding opportunity announcement for the batteries one, we are not saying that we want lithium-ion batteries. We are saying that we want a battery at the cell level, or 400, 500 watt-hour per kilogram, at a cost of $250 per kilowatt-hour. You can make it out of aluminum if you want, or zinc if you want. And so that's our target. I mean, we don't want to pick technologies, we want to pick targets. So I don't know, does that answer your question? Yeah.
Yes, I noticed two of your early investments are in cellulosic biofuels and batteries, which are both areas where there are supposedly early commercial or pre-commercial activities. Car companies are supposed to be bringing us a whole bunch of electric cars in the next few years. It kind of raises the question of how well are those technologies really developed now, and what is the appropriate pathway for deployment through early deployment through the advanced technologies?
Yeah, so I think we have invested in battery technologies and biofuels, but we have invested in those where, frankly, there were no investments in that particular space earlier, and where we saw an opportunity that this would really leapfrog over today's approaches. So those are the investments that we have made, whether it is, macroalgae biofuels, which are a completely different feedstock than cellulosic. So that's a different way of approaching the problem, which essentially creates competition to today's current different approaches to biofuels or batteries, which is good. In terms of scaling and demonstration, that's an issue that we had a long chat today about this. There are other parts of DOE, the applied offices in particular, that are involved in demonstration projects, whether it's carbon capture demonstration or engines and batteries, et cetera. So that's why the coordination of ARPA-E with other parts of DOE is absolutely critical. There are various reasons for coordinating very closely. One is how do we transition technologies to demonstration projects. The other is the fact that all our program directors are going to be there for a maximum of 4 years. We need some institutional memory so that we don't repeat the mistakes and we can leverage some of the things that have been done in ARPA-E and other parts of DOE. So that is where the coordination comes in, and so that's what we're trying to do.
Are you considering geoengineering ideas as an alternative or complement to carbon mitigation?
Yeah, we are. I mean, we are open to it. We have looked at, or I don't know if we have looked at, but I've read a lot of different approaches to geoengineering, and I think it's worth looking at. The issue would be cost. The other issue is that geoengineering obviously is looking at things at the whole world scale. It is very important for us to make sure that if we do at that scale, that we understand the consequences of that. Frankly, we don't quite understand how climate change is happening today. Okay, if you ask the question, do we understand everything? No. We're looking at data, and we're looking at the fact that the temperature, average temperature is increasing, but how it changes climate. Do we understand the ocean currents and the mixing in the oceans? Not quite. We don't understand nucleation of clouds, aerosols. So we don't understand that. So I would say that I think one should consider geoengineering, but before we get into it, we better know what we're doing. Because if you're trying to take two big numbers and subtract them and expect a predictable answer.
In the news today, we're hearing about the Gates Foundation's new building they're putting in downtown Seattle, and they're spending about $500 million on it. In context, spending $4 million each on 34 projects seems completely small potatoes. Is the ARPA investment limited by DOE money, by Congress? When we're giving $10 billion out to banks, right, and you're able to come up with $120 million for something so important, it seems out of scale.
Well, thank you for saying that. Please go to Congress and say that. No, but I think here's the thing. Yeah, this needs to be scaled. We are, I think, as I said, we're not short of good ideas, but the budget is really issue of the president, the executive branch, and the legislative branch. And what I can say is that regardless of what the budget is, we will make the best use of the money, and see the biggest difference we can make with whatever we have.
Yeah, I have a question here. Energy and emissions are all correlated. The more energy we need, or more energy we use, more emissions we have, usually, whether it's coal or electrical power. Now, is there a focus for ARPA-E to reduce or improve the energy efficiency now so that we can reduce the emissions? Or your focus is more creating innovative ideas 5 years down the road? Or are you focused also to something now, available now? Is that?
Yeah, I mean, I think it's both. The balance is important. We are looking at innovative ways of, and as I said, rewiring that energy spaghetti chart, right? How do you take sunlight or electricity, for example, and turn that into petroleum? If you can, that would be rewiring the diagram. I mean, that's required. That's absolutely something that we want to sort of change the ball game in that sense. But there's a need. I mean, we haven't really invested in energy innovation for a while. And there are many industries that that needs help in reducing the energy consumption, in producing energy more efficiently. I'll just tell you that in coal-fired power plants, the efficiency of the plant, the thermal efficiency of a plant in the United States is about 35%. In Japan, it's 41%. Right? Now, that 6% is huge if you look at the magnitude of energy. So what is it then? It's the design of the plant, it's new materials. High temperature materials is very important, especially for gas turbine energy conversion, both for traditional gas turbine and also for nuclear for that matter. So these are the things that there are gaps that we have, they exist today, and we have to address that. But we also look at sort of futuristic ones. Yeah.
I had a very similar question, and it related to about 10 years ago, we all switched to fluorescent bulbs in our houses and that kind of thing. And I look behind you and I see a wall of LEDs, which is kind of ironic for this conference, but
Oh, that one. Okay.
Yeah.
Well, that's cool.
yeah, it is cool. But, you know, the idea seems to be focused in on energy generation and not energy reduction. And that's just my observation. And it seems like there could be more emphasis in that area. Are these 37 proposals, of those, how much are related to energy reduction versus energy production?
Yeah, I believe there is one on buildings. There are several on batteries, which are potentially energy reduction because the efficiency of a coal-fired power plant or a power plant, thermal power plant, is higher than that of an engine. But you're right. I mean, I don't think we have invested enough on the demand side of energy, the energy efficiency, energy reducing the demand. I talked about the buildings example that requires technology. And there needs to be a balance between the two. It's hard to say. I mean, there are supply side people say we all should go for renewables. The demand side people say energy efficiency is everything. I take the viewpoint you need both. You can't do one or the other. And the balance is important.
I'm wondering if ARPA-E is also looking into all the ways that we dig up fossil fuels but don't use them for fuels, like fertilizers and plastics. Is that ARPA-E's department or is that someone else?
Yeah, I mean, at the end of the day, it's reducing greenhouse gas emissions and on energy. I mean, those three axes are decided by Congress. I mean, it's go after these three axes and figure out how we can provide energy security for our country, reduce greenhouse gases, and use technological lead. So yes, petroleum for other products has energy security issues and greenhouse gas emissions issues. So absolutely, yeah.
Thank you very much.
Great, thanks a lot.